Hi, my name is Malia Robinson, and this is my presentation about memristors. So first, we're going to look at what a memristor actually is. So it's called a memristor because it is a memory resistor. It is a resistor with memory. It is a nonlinear component, so the IV curve is nonlinear, unlike the regular resistor. And we will see these curves in the simulation results. It has non-volatile storage. It remembers data even when the power is off, which is very useful for this kind of component. It follows a variation of Ohm's law, and we know Ohm's law from the regular resistor, which is V equals I times R, but here it's a little different. So here in its simplest form, the mem resistance is V, which is the voltage, equals M of Q times I, which is the current. So that M of Q is not a constant. It is actually a function, and M of Q is the function of quantity of charge that is passed through the device. So since it's a function, the values will vary, which is very unlike the regular resistor that only has one resistor value at a time. All right, here we can see the diagram of a memristor, which is in the bottom right, and that's in relation to the other basic circuit components. So it's called the fourth basic element of a circuit. Before they found the memristor, it's pretty recent, they had this missing piece there. They knew something had to relate electric charge and magnetic flux. They didn't know until they found the memristor that that link could actually be filled. So, like I just said, the memristor relates the electric charge and the magnetic flux. All right, we're going to look at the effects of doping on resistance. So this is how a memristor works. So we have a boundary, that's the dotted blue line, and on one side, on the undoped side on the right, we have your run-of-the-mill titanium dioxide. And on the other side, we have TiO2 minus X. So the minus X there means that there are less oxygen atoms than the right side. And this actually conducts current better. The dope side conducts current better because it has less oxygen atoms. So the boundary, whenever it moves because of the current flowing through the device. The mem resistance is either going to increase or decrease. It's going to increase in mem resistance when the boundary moves to the left. So that means whenever the doped region is smaller, it will have more resistance in our memristor. So I used NanoHub to simulate a memristor. The tool I used was the Memristor simulation tool, and I only changed one parameter. I changed the voltage. I changed the voltage because whenever you increase the amount of voltage applied through the memristor, it will change the amount of current passing through the device, which will yield a different IV curve each time, which we'll see in the simulation results. And with the changing voltage, we'll also see its effects on the mem resistance. So all the other original parameters were kept the same. The other parameters I could have changed were the resistance when the device was on and when it was off, the thickness of the device, the average carriage mobility, and the frequency. But I just changed the voltage, and we'll see what that did. Alright, here's my simulation results. We're going to look at the IV curves first. So if you look at the 1 volt, this is the smallest voltage I applied to the memristor. It kind of looks linear, but if you look very close on the edges, you'll see that there's kind of like a bulge there. And with the 5 volt, you can see that that's what it would look like if you could zoom even closer, that it is nonlinear. Alright, and for the 10 volt, you can see that there are more lines. There's different curves there, and that's because of the M of Q function. So since that's a function, we'll have different curves for the different inputs of the M of Q. Now on the 20 volt, we'll see that that's kind of flipped from the other ones, and we'll talk about that more in the analysis. Alright, so here are the mem resistance versus time graphs. So for the 1 volt, you can see that the range is smaller because there's a smaller voltage, and whenever you increase the voltage, the range starts to increase. So you can see with the 5 volt, the 10 volt, the range has increased. It just looks a bit smaller because I didn't zoom in as much. But you can see that it is increasing the range, but it's also increasing in amplitude. And on the 20 volt graph, you can see that it looks like it's decreasing, but actually it is increasing in magnitude. So the magnitude is increasing with a higher voltage. And I think because of this, it looks like it's decreasing, but it's increasing in magnitude, is why this 20 volt IV curve is flipped from the other ones. It's because that M of Q function has negative values. Alright, let's look at the analysis a little deeper. So we saw that in the IV curves, since the voltage was increased and all the other parameters were kept the same, R on and R off were kept the same, the voltage increased. So why did the voltage increase? Well, this was to be expected because of the equation that we saw in the beginning. It's kind of like Ohm's law, the V equals M of Q times I. So the increase in current can be seen in IV curves, which is what we saw. So let's look back at that. So if you look at the 1 volt, the current on the y-axis is very small. It's in microamps. And then with the 5 volt, you can see it's increasing just a little bit. And the 10 volt, it increased again. And with the 20 volt, it is much larger current than the current we saw in the 1 volt IV curve. So we just saw that the current increases with the increased voltage. And also, when we look at the mem resistance versus time graphs, we can see that the range of values of the resistance function, M of Q, is increasing, but in magnitude. So we saw that whenever we went through those. But why did it do that? This is because of the equation that relates R off on R on and the charge. It's M of Q equals R off times 1 minus K R on over D squared times Q of T. But remember I said that I didn't change any parameter except the voltage, right? So why did the range of M of Q increase? So this is because, so Q of T is a charge, right? Which is a function of current over time. So since we saw that the current increases with an increasing voltage, the charge also increases because charge is related to current. So since that charge increased, there are a wider range of values for the mem resistance function. And we saw that in the mem resistance versus time graphs. So in conclusion, the memristor is the 4th basic circuit element, and it relates magnetic flux to electric charge. The mem resistors work by using doped and undoped titanium dioxide. The current passing through the mem resistor shifts the boundary between the doped and undoped titanium dioxide, which results in different resistance values. And in the simulation, we saw that the current increased increases with the increasing voltage, and that the voltage that increased affects the charge function, which in turn affects the memresistance function, M of Q. Here's my references. That was my presentation on memristors.